I welcome you to the second part of our training on UV visible spectroscopy, and today we shall continue from application of Woodward-Fisher rules for calculation of landmarks. Robert Burns Woodward and Louis Frederick Fisher in 1945 and 1959 respectively are the great scientists who has worked on the establishment of Woodward-Fisher rule. Woodward gave some rules which correlate the molecular structure to their landmarks, and Fisher in 1959 modified these rules, and from their assignment they find out that each type of diene or triene system has a fixed value at which the absorption takes place, and they have these fixed values are regarded as base value or parent values. So for you to obtain the total wavelength or maximum wavelength of absorption of a compound, you have to put into consideration the base value as well as contribution made by some alkyl substituent or ring residue, as you may call it. We may also have contribution from double bond extending conjugation, polar groups, and all this has to be put in place. Let's look at different structure as they proposed. If you look at structure one here is regarded as a form of diene which is regarded as homoannular diene. Structure 2 is heteroannular diene. Structure 3 we have endocyclic double bond, and structure 4 we have exocyclic double bond. So it is possible that you have heteroannular diene which also has a contribution of exocyclic double bond, and just like as if you are drawing, if you have two double bonds in which the double bond from the other, you have two rings in which double bond from the other ring is adjacent to the first ring, okay, it become an exocyclic. Just as the name heteroannular means that you have two rings as well, and the double bonds are in different rings, conjugated anyway. So you could see their definition here. A cyclic diene having conjugated double bond in the same ring is what you refer to as homoannular. The heteroannular have the conjugated bonds in different rings. You have endocyclic double bond in a ring, and you also have exocyclic double bond. And now if you look at structure 4, as I was explaining, ring A has one exocyclic double bond because the double bond from ring B is just adjacent to that of ring A, and it also has one endocyclic double bond. So ring B has only one double bond, which is an endocyclic double bond. I try as much as possible to gather some values, table of values for Woodward-Fisher rules. Okay, so you have conjugated diene correlations, and you have base value for homoannular. If the diene you have is homoannular diene, the base value or the parent value, as I've explained the other time, is given as 253 nanometer. For heteroannular is 214 nanometer. A key substituent or ring residue which is attached to any parent diene has a value of 5 nanometer, and double bond exchanging conjugation, that in that sense, that means you have more than 2 double bonds. Okay, you have conjugation existing between 2 double bonds which has a single bond in between them. I hope as a student of organic chemistry you know what isolated double bonds are. Conjugated double bonds, you know what they are. So, and we have values for polar groups and so on like that. So the table continues on this page 21. The table continues. Page 22, you also have the continuation of the table. Page 23, it continues. So you can take your time to look at those values for base values for aromatic compound and other contribution that could be made by alkyl groups, maybe in auto, meta or para position. So the O here, number 4, where we have polar group, you have OH and OCH3, that is hydroxyl and methoxyl group, and O alkyl. Okay, so depending on where they are, in O, that is auto position, that we are talking about a ring system now, in meta position, in aromatic ring system, and so on like that. So you can take a look at the table. Let's move on. So the continuation of table still extend to this. So let's go to real business and see some few examples which you may give a try, or if you also have any structure that you want to calculate the lambda max, you can make use of the table and then compare. If you look at this, this has a base value of 214 nanometer. I guess you know that is heteroannular, and it has a beta substituent. The contribution is 12 nanometer. You may go back to check the table. We have delta substituent and double bond extending conjugation. Now we are having more than 2 double bonds here, so the third double bond is also conjugated, so you have that. Exocyclic double bond is also present, 5 nanometer, and total land mass of the structure in example 2 is 279 nanometer. Let's check example 1 here. By my right hand, you will see the base value is still heteroannular diene, is 214. Ring residue, a key substituent. Okay, you could be looking at that. In between the 2 rings, there is a bond where the 2 rings joins to. So if you look at the caricature of that bond or of that ring, you will discover that there is a single bond that goes up in between the 2 cyclic ring, so and is regarded as ring residue. Depending on where the ring residue is present, you may have it on a long chain as well. But identification of ring residue is very, very important. You could check to have more understanding. Does it have exocyclic double bond? Yes. The ring by my left hand has a double bond, and the double bond is just adjacent to the ring by my right hand. So if you check, okay, it's that double bond is exo to the ring by the right hand. Okay, so and it has a contribution of 5 nanometer. The total maximum wavelength of absorption was summed up to give 234 nanometer. If you check example 3, I wish you go back to the table of values to check the base value, which is 246 nanometer. We have ring residue in auto position, which has a contribution of 3 nanometer. We'll have a polar group, that is methoxy OCH3 in a para position, and the maximum wavelength of absorption rate 274 nanometer. Okay, example 5. If you look at example 5, the base value or parent value is still heteroannular diene. It has ring residues. I'm saying residues now, not one. And if you count that, you have 5 ring residues. Okay, one in between ring 1 and 2. I'm starting by my left. Okay, after the ring 3, where you have double bonds, there is one cyclopentane that is attached to it, and after the carbon carrying double bond, it's as if you have a tree-like or a Y-like bonds. So each of them they are ring residues. So if you count those, that is 2 plus 1 we have counted. So if you check thoroughly, you will find out we have 5 ring residues. I could have been pointing to this, but the pointer is not actually, it's not going to be showing what I expect for you, so I could have been doing that. So just find a way to understand what a ring residue is, so that you'll be able to count. So, and example 6 as well is just heteroannular diene, and it has 3 ring residues. Okay, which has a contributory factor of 15 nanometer, and we have one exocyclic bond, double bond, okay, on ring 2, and the total wavelength or maximum wavelength of the structure on example 6 reads 234 nanometer. Let's move to interpretation of UV spectra. Don't forget, we are dealing with UV visible, so sometimes we may be convenient to mention UV spectra or spectrum, but that doesn't mean that you cannot have absorption of the visible region on the spectra. So now, from previous studies that you have been told that the independent use of a single spectroscopic method cannot give an accurate or confirmatory answer to what your structure is. So we still put a note here that the independent use of UV spectrum as the only method for extracting quantitative information, qualitative information about a particular compound is always difficult. It's often difficult. So we advise that you combine other methods such as infrared spectroscopy of Fourier transformed infrared spectroscopy, as well as NMR, in order to have a general idea of certain group of compounds that are present. And in short, we call it joint elucidation of structures. So you may have carbonyl, double bonds, aromatics, ring system, nitro group, nitrile, enones, and the likes. So if NMR and the IR data are available, it will help to juxtapose or to determine the accuracy of the value we have from UV visible spectra. Now we try to give a table of values which is not commonly available anyway, but we just managed to extract that from previous literatures. We have a column for absorption band, the intensity of absorption, the molar absorptivity, and wavelength, and the type of transition that may be possible around that area. If you have a single absorption band and the intensity is low to medium and the molar absorptivity is between 100 to say 10,000, and the wavelength is less than 200 nanometer. In our previous studies, I hope you remember that we talked about that. So the nature of transition that we could have here could be non-bonding to sigma star transition, and you could have that from the amines, nitrogen being bonded to hydrogen, hydroxy group, the carbon monoxide, as well as maybe from thiols. So provided that the non-bonding electrons are not included in conjugated system. So in our case, if the molar absorptivity is less than 100 and the wavelength of absorption is less than 220 nanometer, you could have a weak N to pi star transition, which is possible in nitriles, containing compounds. So if in other case you have a single absorption band and the intensity is low and you have absorptivity between 10 to say 100, the wave absorption is between 250 to say 260 nanometer, and you don't have a major absorption, okay, at 200 to 250 nanometer to a shorter wavelength or at a longer wavelength. So if you don't have any of that, we could be suspecting the non-bonding to pi star, which you see in those functional groups that are listed. If the type of band you have two, and the intensity is medium, and you have the absorptivity between 1000 to say 10,000, and the wavelength, maximum wavelength, is above 200 nanometer, you could be suspecting the presence of aromatic system. And if it is above 10,000 nanometer, you could be talking about a substituted aromatic substrate, which increases the conjugation, and perhaps you may have appearance of a third band, okay, near 200 nanometer, which may be talking about polynuclear aromatic with characteristics, intensity, and band shape. So if the number of band you also have is 2 and you have a medium intensity with absorptivity between 10,000 to say 20,000, and the maximum wavelength is above 210 nanometer, we'll be talking about alpha beta unsaturated ketone, diene, or polyene. So a longer wavelength indicates that there is a more conjugation in the pi electron system. So we still giving a note here. So to specifically say the nature of the functional group of which band you are observing, it is advised that other methods such as infrared spectroscopy, nuclear magnetic resonance, they should be combined with UV spectra so as to validate the presence of chromophore. So to validate that, you may just need other spectroscopic method. In the visible region, they compound with distinct colors. Okay, they appear in they absorb in the visible region, and we try to give different types of chromophore that you can have here: long chain conjugated system or polycyclic aromatic chromophores. Okay, you could have benzonal compound with colored if they contain enough conjugation system. Some non-aromatic system with a minimum of 4 to 5 conjugation chromophore could absorb in visible region as well. We have some compounds which are not aromatic, but they absorb in the visible region of electromagnetic UV visible. They absorb in visible region of the electromagnetic spectrum. Examples such as lycopene, beta carotene, they are good example of that. So we have other compounds that could absorb as that. So let's move to the next slide. Here we want to show you a few examples of the spectra. Okay, we try to label them 1, 2, and 3. You see this compound called isoprene here. Okay, isoprene, which is 2-methyl buta 1,3-diene. Okay, so the concentration at which they were taken was stated to be 4 times 10⁻⁵ moles per liter, and the path length of the cuvex was stated to be 1 centimeter. So that compound, by stating the concentration at which the sample was run, gave a maximum wavelength of 222 nanometer. You could see something here. The spectrum 1 and the spectrum 2. Okay, they present the same compound. So in plotting the graph of UV visible spectrum, you could plot the molar absorptivity against the maximum wavelength, or you could obtain the absorbance against the maximum wavelength. So now, from your Beer-Lambert law, if the concentration is known, you know the path length of the cuvex, you get your absorbance, then you can determine what the molar absorptivity is. So that's the beauty of the machine. You prepare the concentration by yourself. The cuvex you are using, you know the path length of the cuvex, so you can easily get the absorbance. And the moment you get the absorbance, it becomes easier. By substituting those values, you get the molar absorptivity. So to obtain the values, or to interconvert from molar absorptivity to absorbance and the likes, just play around your Beer-Lambert equation. So let's look at the spectrum 3. Okay, we gave a general compound RCH double bond CH into bracket NR. Okay, as much as you increase the number of the CH double bond CH chain, you are trying to increase the conjugation. Okay, when you have your hand to be equal to 3, you could see a green absorption band. when you increase the number in the chain, okay, you have n equal to 4, there is a shift to maximum wavelength. And I hope you remember that from our previous class. That is what? A bathochromic shift that you call red shift. Okay, so if you increase it more to 5, you have your absorption band also increasing, and that's confirm a statement in previous class that increasing the conjugation would always increase the maximum wavelength of absorption. So we try as much as possible to give the spectra of another compounds here. Okay, you have naphthalene here, you have anthracene, and you have tetraene. Okay, those are multiple aromatic ring system, and the color is used to indicate, okay, the bands. So you could see that as much as the aromatic ring system, the number of ring system increases, what happened to absorption band? There is a shift to a maximum wavelength. Let's check the structure 5. Okay, that is heteroannular diene. You remember that? Okay, we have exocyclic double bond here. You remember that? We have ring residue or a key substance, so to say. You remember that? So if you check the value, let me still inform us that there could be a little variation in the observed maximum wavelength of absorption and the calculated. So other factors may influence that anyway, but there could be just a little variation. Okay, a factor of numbers, little variation in the maximum wavelength of absorbed, the calculated and the observed bands. So ladies and gentlemen, I want to appreciate you for your patience, especially for the completion of our training on application and principles of UV visible spectroscopy and interpretation of spectra. So you may go over our you may watch our video over and over again to have more understanding to all we have explained. And in case you have any question, you may channel your question through Noble Mind groups. As much as possible, we will try to attend to your question. Thank you very much. These are the few resources or source materials that were consulted. I thank you. God bless you.